All right, so let's talk about, let me just bring this up. All right, so there's many proofs in this section, and some are left for the independency. So they just go through, this is just a section of proofs, and it's just a lot of proofs, right? And we're just not going to go through it all, right? It's a long slog that really doesn't help you as engineers. And for mathematicians, you better believe we'd be digging through it, right? But this isn't the math one. This is the engineering course. And so basically it boils down to, what do we care about? We just, given, so in this section, we're focusing on homogeneous linear ODEs. And so we want to know if it exists and it's unique for initial value problem. And so basically all you need to care is that P of X and Q of X are continuous on an open interval I, and that the open interval contains your initial condition, right? So as long as both are continuous, you're fine. Let's talk about what it means to be linearly independent. Linearly independent means that if I add two of them up, that C1 and C2 had to be 0, right? And it's linearly dependent if I can write one as a multiple of another. This is kind of boring for the two-dimensional case. For the two-dimensional case, if one's not a multiple of the other one, it's linearly independent. That's all that's required. Is one is not a multiple of the other one, and 0 is not a solution. It's not a linearly independent solution. So a lot of our solutions, let me just explain. Let me talk about 0 for a second. So let's talk about linearly independent. Let's talk about linear independence real quick. So here, if I have y equals to x squared, and then, so if I had y1 equals x squared and y2 equal to x 3x squared. These are linearly dependent. These are dependent. Why? Because if I just multiply this one by 3, I get that one. But if this is y1 is equal to x squared and the other one's y2 is equal to x to 2.1, or x to 2.1, these are independent, right? Because one's not a multiple of another. AKA, here if I have c1 y1 plus c2 y2 is equal to 0. Well, if x is 0, that means C1 and C2 could be anything, but this needs to be true for all x's, right? So here, when x is not 0, and this is for all x, And we're going to just run x through the rails just for kicks. You guys seen this symbol before? The upside down A? It's for all. Yes, no, maybe. Some of you. And so this has to be true for all x's. So even though if I plug in x equal to 0, I don't need C1 to C2 equal to 0. So this is what it means to be linear independent. If you take a linear algebra class, you dive into linear independence ad nauseum. For us, it just means that one solution is not a multiple of another. So in order to solve our initial value problem, right, where I have y double prime plus ax y prime plus bx y equals 0, where I have y of x sum naught equals y naught, and then y prime of x naught equal to sum y prime naught, or y naught prime, or y star, right? Y naught star, just another solution. If these are linearly independent, if this is not the same as this, right, then the whole point of this is then no matter what initial conditions I give you, you can solve for it, right? You can solve for no matter what initial conditions are. If they're linearly dependent, right? Say if I had this and this, there would be a lot of initial conditions which would not have solutions. They just wouldn't. And so that's why we specifically look for two linearly independent solutions. And according to the theorems in the books, as long as P of x and Q of x are continuous, these two linearly independent solutions exist, right? Not only do they exist, but they're unique, right? And they're unique up to a constant, okay? So then your book defines this. Well, here's a Wronskian, right? So we're going to say y1 and the derivative of 1 minus phi 2 is the derivative of 2. And we're just going to say, and it's come from the following matrix. And the reason I show you this matrix is useful when we're dealing with higher orders. We deal with higher orders, you just take the derivative of that. Right. And as long as the Wronskian is not equal to 0, that means for some x in the interval, that means your solutions are independent. And so here I just run through a quick solution with you. So here we have y equals omega squared. Here we know what this is, cosine and sine. And here I'm just showing you a quick brief. If I plug it into the Wronskian, which is this, where it's the Wronskian is just the first solution and its derivative, its second solution and its derivative, then you take the determinant. Here we pull out the w. This becomes cosine squared plus sine squared. It doesn't really matter what this is. This is always 1, so this just is equal to w. And as long as w is not 0, there it's linearly independent, right? Hold on. Ooh, hi. I lost my mouse. Where'd my mouse go? There, I scored my mouse back. And then here we can say that these solutions are linear homogeneous, and that also satisfies the Wronskian, because if I do that, this is perfectly fine as long as m1 doesn't equal m2, right? Because when x is 0, yeah, this does equal 0, but for x, any non-zero x, as long as this doesn't zero out, we end up being this. And so this is, the Wronskian is just a fancy way of testing for independence. Now, this may not seem that interesting for the 2x2 case, because it's not. It's just not. It's not interesting for the 2x2 case. But when we do later, for the 3x3 case, it becomes very interesting, right? I used to make general solutions that known in brevity. So if this is, and these are continuous on an open interval, every solution has this form, right? And so basically this is just, once we prove there's 2 linearly independent solutions, right? And we can always find them, and that we can solve any initial condition, we prove that this is not only the a solution, not only a solution exists, it is the only solution, right? And so there's no other singular solutions. There's no other singular solutions that you cannot obtain. You cannot attain except for attain that's not in the general solution. So there's nothing else out there to look for, right? That's all the whole point of this is. And this can be extended to higher orders. That is the whole point of this section. It's not hardly interesting. And then so all you're going to do in the homework is just do a bunch of Wronskians and test this. Now I do say no singular solution. That's not entirely true. Y equal to 0 is kind of a singular solution, but it is of this form, technically. It's technically of this form, right? Because here if I set of y1 plus c2, y2, notice if I set c1 equal to 0, c2 equal to 0, that means y equal to 0. So it is, even though it's not, it's kind of a strange solution, it's not a singular solution in the sense that it doesn't come from this form. Okay? And so basically all this is saying, you do this weird little Wronskian where you just test for linear independence. It's not interesting in the 2x2 case, but let's pretend I had 4 different trig functions, and I want to prove all those are linear independent. Like, it's a little bit more complicated, and the Wronskian will allow you to show that. Okay, so in the 2x2 case, this isn't all that interesting. We'll just go through it. All right. Yeah. So that's the first 2 set of notes. We'll just do